Hi, welcome to the week 10 session for Introduction to CFD. So this week's discussion was mostly based on multi-phase flows and particularly multi-phase systems with continuous phases together. So there was no there was not much discussion upon the discrete phase systems, which are basically like particles suspended inside a continuous medium. Anyway, so this sort of a flow was like considered the most important in this discussion for for this week, and this is known as a separated type flow. That is, there are two continuous media 1, media 2, and they're separated by a continuous interface, which is like this. So then tracking or capturing this interface, basically locating this interface is an important problem in the CFD for multi-phase systems, and there are various methods by which this is done, which can broadly be classified into two categories, that is interface capturing and interface tracking. So what the salient difference between these two methods is that with interface capturing, what we try to do is that we take a function, it's typically called the color function, and we just try to see how that function varies and then reconstruct that interface. So the important word over here is reconstruct. Meanwhile, for the interface tracking method, we begin with a particular interface and then we stick with it and we see how it evolves over time. So basically, the difference between the interface capturing and interface tracking is that wherein the interface is reconstructed when we are dealing with capturing, and we try to again build up the interface from whatever information we have. Whereas for interface tracking, we begin with a known interface and then see how it evolves in time. So this is the difference. Right. Um, then now that this is just a brief introduction into whatever has been discussed. So various methods were also talked about. One was volume of fluid, another was level set, and the CIC, and etc. So then these were all discussed during the lectures by the professor. Right. So we'll move on to the questions now. Okay, let's have a look at what the first question says. The first question says that an infinitesimally thin phase surface S. Okay, so we have a surface S over here, which you can see, separating two incompressible viscous fluid regions is shown below with the unit normal vector n. Okay, so we have a unit normal vector n. Okay, the interface velocity is v. The velocity of the interface is v, and the normal component of the interface velocity is vn. Okay, the fluid next to the interface in phase 1 moves with the velocity of u1, and the fluid next to the interface in phase 2 moves with the velocity u2 respectively. Density of the fluids into two phases is ρ1 and ρ2 respectively. Assume that there is no phase change occurring at the interface. The velocity jump conditions across the interface is given by. So this is something that was discussed also in the lecture notes. So the jump condition for if our interface like this is basically that the velocity u1 is equal to the velocity u2. So basically at the interface at this point, the velocities are continuous. They have to match. That is a requirement. That's a physical requirement. So automatically option D is correct. And then option B is also a representative of the same statement. So then the answers for this question is B, comma D. Right. So then moving on, tracking the fluid interface in a region with fluid velocity u using a marker function is performed using the following equations. So here we are talking about a method which is going to be interface tracking, not interface capturing. Okay, because here we are dealing with the marker function. So how is it governed? So it's governed using the basic equation that is used for all other conserved variables as well. That is, and we know that this can also be written as df by dt plus u dot third. Um, u dot gradient of f. So then for this this question, the answers B and C are correct because both of these cases represent the same equation, which is this, right? So once again, this is an interface tracking type of a method, right? So then, um, moving on to the next question. Now here, we are being asked, sharp interface capturing is possible using. So you have to tell where interface capturing is possible. So here we are talking about capturing, not tracking. Okay. So in capturing, we had learned that volume of fluid method and CIP method. So CIP method is basically like volume of fluid only. But then what happens over there is that we use a cubic function to make our interface smoother, right? So these two methods are capturing, and then sharp interface can be captured by volume of fluid, and indicator level set is uses a marker function. Right. So then sharp interface capturing is possible using volume of fluid and CIP. So these both are capturing based methods. Okay. Then we go on to the next question. The advection of the color function is governed by, let's write down the equation, dc by dt plus df by dx is equals to 0, where flux function is given by uc. So we'll just stick to uc. And this c over here is the color function. Where flux is given by f is equals to uc. C is color function and u is a constant velocity in an incompressible flow field. In the above equation, if the above equation is integrated as this, the solution suffers from. Okay, so here basically what is happening is that we have written, the dc by dx as ci minus ci minus 1 whole by delta x, right? So when we are doing this at the face, this is happening at the face. So what happens is when you have two cells, let's just make two cells. Right. So these are two neighboring cells, and we need to find out the value of the flux at the at the wall. Sorry, at the interface, at the face. So this cell is I, and this cell is I minus 1. Let's write it down in the color. So when we are writing down the dc by dx as ci minus ci minus 1 by delta x, we are basically using a um, central difference method. So when we are doing that in this condition, um, what is basically happening is that this equation is similar to is a hyperbolic equation. It is similar to whatever we've seen in the past. So when we are dealing with a hyperbolic equation and central difference, there is an artificial diffusion term that enters the problem, right? So this is the right answer. This has been discussed also in the lectures. Hmm. Right. Okay, moving on. The next question. So over here we have an image, shows two cells J and J plus 1, and there's a constant flow velocity of 1 meter per second. So this flow over here is moving at 1 meter per second in a 1D advection problem. Okay. The relevant parameters are delta x, and we are given the Cj. The condition is the condition 0, like basically we want um, the interface, this green interface, let's mark it with the same color. Right. So the condition Cj plus 1, that is the color function in the cell J plus 1, varies from 0 to 1, then it is fulfilled if the time step delta t satisfies the following condition. So what is basically this condition saying? Like, what are we being asked? We're being asked for the interface to lie somewhere in this J plus 1 cell. So right now it's in cell J. So basically this is like of course the interface will when the interface is not inside J plus 1, that is there is no fluid inside J plus 1, it the Cj, that the color function in J plus 1 is going to be 0. So that's nothing. So I think that this equality is not really supposed to be there, because like until unless the interface lies inside the cell J plus 1, the color function is not going to attain any other value except 0. Right. So basically what we want in this question is that just forget about the equality. So it is asking us um, to find a time step delta t such that um, in the next iteration, taking the next time step, interface lies in cell J plus 1. Lies in cell J plus 1. So this is what is required of us. Basically it is asking us to locate this, like come up with the time steps wherein the interface will lie somewhere around in this cell. Okay. So then the limits for it is it are key, the interface will be at this particular phase or it will be at this particular phase. So let's see how that will happen. So for the interface to enter the J plus 1 cell, it needs to cover this distance, right? At the very least, it needs to cover this distance, that is whatever is left of delta x, and at the very most it must cover this entire distance. Okay, so basically limiting case 1, is distance to be traveled. So one thing to note importantly over here is that this is a constant flow velocity and it's a 1D problem, right? So if we are told that the Cj is 0.35, that means that this region is 0.35 into delta x. Okay. So and therefore by extension this will be 0.65 into delta x. So the distance to be covered for for interface to be at phase j plus half. Okay, this is phase j plus half. This is the same nomenclature that we have followed elsewhere. That this is j plus half and this is j plus 3 by 2. Okay, so for that to be done, the distance to be covered is 0.65. That is the rest of the distance in the cell, like the area in which the fluid is not there for the cell, and multiplied with the delta x. So how much would that be? 0.65 into 0.1 meter, 0.065. Okay. So then let's see how much time it will take to cover this distance. So then 0.065 is equals to u into delta t, and by this we will find out the delta t. So we will basically have 0.065 by 1, because the speed over here is 1 meter per second and is equal to delta t. So our first condition is that the time step should be like the limiting case number 1. For the limiting case number 1, that is when the interface is lying just at the cell face, we have the delta t is equals to 0.065. Okay, this is the smallest time step allowable for a problem to be satisfied, for a condition to be satisfied. Then limiting case 2 is that, let me just write down again. Interface is at j plus 1 half was our limiting case number 1, that is the interface lies over here. Limiting case number 2 is that the interface lies at the other end of the cell, the j plus 1 itself. Okay, so for this we're going to have j plus 3 by 2 is the face at which the interface should lie. So let's see how much distance is needed to be covered. Distance to be covered distance to be covered for interface to be at phase j plus 3 by 2. Okay, so over here it will be 0.065 into delta x, that is this distance plus this distance, so plus delta x. Okay, so that would make it 0.65. This is the color function c, the leftover 1 minus c. This is 1 minus c. 1 minus c in cell j. Right. And delta x, as we know, is 0.1. This is given in the problem. So the total distance to be covered is 0.165. Delta t max therefore is 0.165 is equals to u into delta t by 1. U is equals to 1 meter per second. This is delta t. Therefore, delta t must lie between 0.065 to 0.165 for the interface to lie in cell J plus 1. Right. So this is our condition for a 1D flow case wherein a fluid is moving from one cell to the other to locate to find out a delta T such that the interface moves on to the next cell in the next time step. So anywhere between these two time steps that we have discovered, the um, interface can be over here, here, anywhere. So if the time step selected is between these two values, right? So next, so the color function values in 9 cells are indicated in the following figure. I hope it's visible. Let me increase the size. I hope it's visible. Whatever questions I'm showing over here. Okay. So over here we are given the color function values for these 9 cells. So basically what the color function indicates is how much of the cell is filled with a certain fluid. So like if we have two fluids, like if we have a cell over here, let's make 3 cells. Let's duplicate this. Okay, so if we have like two fluids over here, let's use a color. So it looks something like this, and so we define that wherever this yellow fluid is, we say that color function is equal to 1, that is it's completely covered by the yellow fluid. Wherever there's no yellow fluid, we say that it's C equals to 0. Okay, so and when we have a value which is intermediate of 1 and 0, the interface, there is an interface in the cell. Okay, so we can tell over here, let's see what each of these cells are telling us about the yellow fluids. So wherever there is 1, we can confidently say there is no interface and it is filled with the yellow fluid. Okay, over here also there is 1, right? So these 3 cells are completely filled with the yellow fluid. We know that this when the color function is 0, basically there should be no yellow fluid in that condition. Okay, 0.2, when the color function is 0.2, we mean that okay, 0.2% of this or 20% of this cell is covered with the yellow fluid. Then it's 0.02, so it's just 2%. That's a small interface might be there. And over here it says 0.85, so therefore this should be something like this. But 0.85% of the 0.85 is the fraction of the cell that is covered with the yellow fluid, and here there is 0.9 and 0.15, right? So this is something that we are looking at. So interface should basically look something like this, approximately something like this. Let's see which of our problems is kind of fulfilling all of our conditions. So the most important conditions are that these three cells are absolute. Okay, here there is no ambiguity regarding what the interface looks like. There is no interface in these three cells. So let's see which of these are which of these images are satisfying our problem. So we see that in B, C, and D, there is an interface there's an interface in these three things. But we can clearly see from our analysis that there should be no interface in this particular cell. So that only option A is fulfilling. So option A is the right answer. Okay. So here we can see that okay, this is empty, like this has no interface, and these three have no interface. So that is right for us. That's correct. Okay. So these three are automatically disqualified because of the interface being present in this cell, wherein the color function is 0.0. Let's not use the yellow color. Correct. Okay, let's move on. Right. A linear interface intersects a 2D square control volume. So we have a linear interface. It's an important word. 2D square volume as shown in the figure. Delta x is equal to delta y is equal to 1. Okay. So these distances we are given. Delta x1. This is also 1. Equation of the interface is provided by this, where alpha is a parameter that needs to be chosen suitably. Okay, so alpha is in our control. Obtain the value of alpha such that the interface covers 50% of the volume. Okay, so here what we are given is that we are given the this normal vector. Let me move the color. We're given the direction in which the interface points. Okay, so basically, if we wanted this particular interface to be at a position such that this blue fluid occupies 50% of the volume, we are going to have to satisfy the equation for, like, this is what our interface should look like. Okay, so right now it is at some other location. This is not the location that we need this location. Okay, what is marked by red. So what can we tell from this straight line? Straight away we can see that the required interface passes through 2 points. So one is 1 comma 0 and the other is 0 comma 1. So this is information that we already have. Okay, by geometric observation we can easily find that this is something that we require. Okay, so let's see what else is given to us. So we are given the equation for our interface. Okay, so let's combine this and this together. So what is mx? Mx is, okay, plus y into my. So here we're going to look at this. This is the my, this is the mx, and 1 by under root 2 into j cap is equal to alpha. So we need alpha over here. Okay. So, right. So what we're going to do is that we're going to substitute, put 1 comma 0 in, let's call this equation 1, in 1. Okay, so then 1 comma 0 means 1 by under root 2, 1 by under root 2 plus 0 is equal to alpha. So from here we know that alpha should be equal to 1 by under root 2. Okay, if you repeat it, if you even chose the other condition wherein, like, if you put 0 comma 1 into this equation, then also you will get the same answer. So this is what you require. Okay. So you have your answer over here. Which option matches? Option B. Tick. Okay. So this is something that you can easily do by just observing your interface, and geometrically you can come upon a conclusion such as this. Right. So then we move on to the next question. For performing volume of fluid calculations, two different domain discretization methods are proposed in the above figures 1 and 2. Okay, so this is sort of a uniform structured grid, and this sort of a grid is, it deforms with the interface. Grid which deforms. You can see that over here, let's just mark the interface in red. So this is the interface. So in the discretization technique number 1, there is the cells all look uniform. They don't have any, they don't really match the interface in any way. But the method 2 that is given over here. So in this case, what is happening is that your cells faces, like the cell boundaries, are aligned with the interface. So this grid deforms with the interface. This also has its own value, but let's see what the question is asking us. Okay. So the two different domain discretization methods are performed in the above figures. So one more information which is important is for performing volume of fluid calculations. So the condition is that the volume of fluid method is being used. What does the volume of fluid method do? Is that it tracks a color function, whatever we spoke about in the previous question. So basically, the C function is somewhere between 1 and 0. Right? So let's say this would be C equals to 0, and this would be C equals to 1. So you can see when you're looking at something which looks like this. Okay, let us give this also a gray color. So that So when you're looking at a grid which deforms with the interface, there is no way you're going to get any other value of C. C is going to be either 1 or 0. There is no other option available for you, right? Because basically what you have done is that you have removed any ambiguity, because the interface is the demarcator between different cells, right? So then obviously this method 2 is not suited for volume of fluid. This has its own value. Someone else might use it for, whoever wants to use a deforming grid or has a capability such as that, they might use it. But for the purpose of using the volume of fluid method, you have to have the grid which looks like the first method. In the above figure, and I'm back to reading the question. In the above figures 1 and 2, to track a phase interface, volume of fluid is used. Color function distinguishes the two fluids in one. Fluid 1 is white and fluid 2 is gray. Okay. Note that the thick curved line indicates the phase interface in both 1 and 2, that we've already noted. And it lies exactly at the same location in both figures. Okay. Pick the correct statements from the following in connection with the above two figures. The grid has to certainly deform to accommodate the instantaneous shape of interface as in 2 for performing VOF calculations. That's wrong. For VOF, basically, we are depending on the certainty that the color function will lie somewhere between 0 to 1. So we need the grid to not deform. A fixed background Cartesian grid can be used to approximate the interface as in 1 for VOF calculations. That's right. If the color function value in a cell is filled by fluid 1 is 0, then the value C for any cell lying in the bottommost row of I is 1. Okay. So, which is the fluid 1? So, this white is the fluid 1. And it says कि when we have like we have a cell which does not have any of the gray fluid, its C is 0. So then what is the C for this row? Basically, asking what is the C for this row. So we've already marked that the C is 1. Why is it 1? Because it is completely filled with the gray fluid. So when it's completely filled with the white fluid, we say that the color function is 0. When it is completely filled with the gray fluid, we say the color function is 1. And when there is an interface, we say that the color function lies between 0 to 1. Okay, so there is some that's how we are able to track that interface exists in that particular cell. This is the correct option. Okay, what does the D option tell us? For some cells lying in the sixth row from the bottom, the value of C is 0.5. Sixth cell. 1, 2, 3, 4, 5, 6. No, there is no C equals to 0.5. Why is it not C equals to 0.5? Because in this row, sixth row from the bottom, let's just mark it in red once again. Wait, no, red is not a good idea. So we have yellow. So then, when we are looking at this row, okay, so we'll see what do the color functions of each of these cells look like. Um, this is one. No, this is not one. This is going to be somewhere around 0.85. As you can see, it's mostly covered with the gray fluid. This will be 1. This will be 1. This will also be something greater than 0.5. C is greater than 0.5 because you can see that the interface over here, like this is the interface, right? Like you can see in red. So this is, sorry. So this is covering more than 0. Like half of the area. So when it's covering more than half of the area, this is half of the area, right? It's covering okay, more than half of the area. So the color function is obviously going to be greater than 0.5, right? Since we see that this is all this area is also a part of the grapefruit. Okay, so that is the wrong option. This is again something that you can geometrically, since the figure is showing you the fluid, how the fluid looks like, you can deduce from understanding what color function really means. Okay, right. I'm just going to put approximately so that we don't get confused later on. Approximately 0.85. Slightly a little bit bigger as well. Right. Okay. Fine. So I hope we have come upon the conclusion that we need a fixed Cartesian grid which is able to give us these intermediate values of the color function, that is between 0 to 1, in order to work with the volume of fluid method. If we have a deforming grid such as over here in 2, basically we cannot apply the volume of fluid method at all, because in this case the color function C will either be 1 or it will be 0. Okay, so that is not giving us any information about where the interface lies, since the grid itself has deformed about the interface. Right. Okay, we move on. So this is the last question that I have today. Right. Okay, this is really grainy, but I'll read it out to you. In the above diagram, the interface between the two fluids is being tracked using. So again, by inspecting visually, we have to tell. So these are the two fluids. I'm going to mark the uh, fluid 2 in gray once again, like the previous problem. Okay. So here, let's see what we can observe. We can observe that there is some red dots which are tracking the interface, right? So they stick to the interface and they keep on, and as the interface will keep on evolving, these points will also follow its deformation. From the above diagram, the interface between the two fluids is being tracked using translating boundary method, no. Immerse boundary technique, no. Front tracking method, yes. So here we are front tracking. We are not front capturing. In the beginning, I did state that there were two main methods by which we have discussed during this week. That is front tracking and front capturing. So whenever you are trying to reconstruct the interface such as that in the previous problem, so over here we are trying to reconstruct. We have a value of C and we are trying to we will not have the interface with ourselves. We will have the values of C. And using those values of C, we are reconstructing. We are redrawing the interface. Over here, we already have the interface. And what's happening is that basically you are trying to just follow the interface. So when you are following the interface, it is called the front tracking method. Okay. So that's all I have for today, and we'll meet in the next week again at the same time. And one important information that I want to give you, it will also come through the main website, sorry, main mail, is that for the 12th week session, the 12th week session by me would be on 11th, 11th October. So basically I'm unavailable on Sunday for the 12th week, so I'll be taking it on Tuesday instead. It's 22, right? Right. Okay. So this will be the last time, like the last session for this particular course by me. Right. Okay. I will now close the session. Thank you for having a look at it.